Hey folks, I hope y'all had a great weekend. Let's go ahead and get started. What we're going to look at today is a theoretical technique for attacking AES. It's called linear cryptanalysis, and it uses the idea of attacking the S boxes to form a probabilistic assessment of the plaintext corresponding to an encoded message. The idea is we won't have an exact break for the code, but if we can come up with enough probabilistic things that we can look at, then we can make some inroads into like educated guesses as to what the plaintext would look like, and that would give us narrow down the number of cases that we would have to check by brute force. That's the idea. So we're not going to be able to do this on AES because, one, AES hasn't been broken yet, and two, the number of rounds would take a very long time. So we're going to look at a sort of a simpler case here. So let's just look at a single S box and say that these are the input bits and the output bits. Perfect secrecy, which we've talked about before, this was mentioned in Shanna's paper, requires that the ciphertext give no indication as to context of the plaintext, so that for any pair of plaintext and ciphertext bits here, the probability that they XOR to be 0 and the probability that they XOR to be 1 should both be should both be exactly 0.5 for perfect secrecy. Excuse me, I've got the hiccups here. We know that an SPN cannot provide perfect secrecy. This is a theorem that we looked at before, and so there has to be some deviation from these probabilities. What we're going to define is the amount of deviation, the probability that some combination of these bits has a value of 0. And again, it's the only possibilities are it could be 0 or 1. The probability that's equal to 0 minus 1/2. And we'll say that's the bias of this combination of bits. So if this combination had a probability of exactly 1/2, the bias would be 0, which is what we're approaching. But if it's not exactly 0, then or not exactly 1/2, then we're going to see some bias. And what we're going to try to find are combinations for which the magnitude of the bias is large, so that the farther away from 1/2 the probability is, the more certain we can be of what these bits should be representing. So let's look at Zig's example here. This is a 4-bit S box. This is not the one that's being used for AES. And if we check these bits here, X2 and X3, so the input bits 2 and 3, and the output bits 1, 3, and 4, we find that the XOR combination of those 5 bits equals 0 12 times and 1 only 4 times. Let me walk through the first few rows here. 0, 0, 1, 1, 0 gives me 0. 0, 0, 0, 0, 0 is also 0. 0, 1, 1, 0, 1, well, that gives me a 1. That's one of the ones that we get. 0, 1, 0, 0, 1 gives me a 0. 1, 0, 0, 1, 0, that gives me a 0. You can already start to see that I'm starting to get a pattern of getting 0 more often than 1s for this combination of bits. And knowing that non-randomness gives me some possible exploit of what's going on here. And so what we can do is, if I know how the other aspects of the SPN work, then I can sort of chain these together from the first round to the last round, and maybe find some combination of plain text and ciphertext, some relation that should happen, and then use that relation that should happen to get some information about the key. So we have this lemma that's called the piling-up lemma. That is, if we are encoding through multiple steps to get from the plain text to the ciphertext, and these steps are independent, and we know what their biases are, then the combined bias of the different steps is the product of all the individual biases times 2 to the n minus 1. So this is I don't want to say bad news. It's expected news, that because you are permuting between each step, you're moving the bits around, you don't expect that the biases are necessarily going to line up in a way that's going to be beneficial to you. And so it turns out that the longer you chain these biases together, multiplying these fractions together, even though you've got this term in front of it, will eventually make these things get smaller and smaller. This is why multiple rounds of encryption are more secure than just a single round. Okay? So let's look at this example for a moment. Let's, for right now, call, because I want to label some of these intermediate bits here as well. So my input to the entire process I'm calling x1 through x4, and my output for the process is y1 through y4. This is a very simple SPN with only 2 rounds. We have an XOR, we have an S-box, we have a permutation here that just takes the bits and reverses them. Then an XOR, then an S-box. Instead of a permutation in the last round, we have a third XOR. Let's call these bits I1 through I4. These bits that come out of the S-box, I for input and O for output. And then for the second S-box, since I've used I and O, I'm just going to go up one letter and call these J and P. Okay? And let's say that we have this pattern, that I1 XOR I4 XOR J1 X, or not J1, O1 XOR O4, that this S-box has a bias of positive 1/4. Okay? And the same thing for this S-box, so that J1 XOR J4 XOR P1 XOR P4, that combination also has bias 1/4. Okay? All right. By the piling-up lemma, these combinations combined, when you string them together, has so I1 XOR I4 XOR O1 XOR O4 XOR J1 XOR J4 XOR P1 XOR P4 has bias 1/8. So how do I calculate 1/8? It's 2 raised to the first. This is n minus 1. There are two different combinations I've got here. So 2 minus 1 times 1/4 times 1/4 is 1/8. So it's a small amount of bias, but there is some bias in this combination here. Um, so let's see if we can simplify some of this a little bit here. All right. So what we have is I1 and I4. These are just X1 and X4 combined with some keys. So I'm going to write this combination out again. I1 composed with I4 got composed with XOR with O1, XOR with O4, XOR with J1, XOR with J4, XOR with P1, XOR with P4. This is X1 XOR X4, XOR with some bits of the key. Specifically some bits of key 1. All right. And I'm not going to write out the specific key bits. O1 and O4. So if this bit is O1 and this bit is O4, the permutation takes them to O4 and O1. And then when I XOR them with the second key, I get J1 and J4. So O1 and O4 is the same thing as J1 and J4 XORed with a key. So J1 is O4 XORed with a key bit, and J4 is O1 XORed with a key bit. So this is O4 XOR O1 XORed with some more key. XOR with P1, XOR with P4. Well, O4 and O4 XOR themselves out, and O1 and O1 XOR themselves out. And when I XOR a bunch of key bits together, that's going to be either a 0 or a 1. And so what we have is X1 XOR X4 XOR P1 XOR P4 has bias of either plus or minus 1/8, depending on whether these keys came out to be 0 or 1. But that gives me a combination whose only difference between Y is the last key. And so if I know that these bits, if I XOR them together, has a bias of plus or minus 1/8, and I get something different down here, then that tells me something about these two bits of the key. That's the idea. And if I can get enough examples of bias, then I have at least a probabilistic ability to guess at what the bits of XR3, the third key, are. And if I can crack the third key, or if I can crack it with a high degree of certainty, then I can work my way back and then just apply this technique again, and then try to crack the second key. And again, this may be a probabilistic attack, but if we could work back up then and we could crack the first key, that's the idea. That we would not know for absolute certain what the XOR3 key is, but we would know that there is a bias in this combination, that it turns out to be 0, not exactly 50% of the time, and so that gives me some possibilities for this. And if I have several different examples of what kind of bias, I've got then I can look at this and try to find what the most likely keys are for XOR 3. That's the idea. For a 2-round SPN, this might be doable. For a 10, 12, 14-round SPN, this piling up lemma defeats us. That if we take these little tiny biases here and start stringing them all together, the combined bias is going to be so low that the probability that you get here is not very convincing. In fact, 1/8 is not super convincing, but if we had enough examples, we might be able to combine them in a useful way. That's much less likely with AES. And that's one of the reasons why AES is still considered to be secure. All right. We'll move on and start talking about hashes next time. Take care.